Second. One more second, please. All right. So welcome, everyone. Welcome again to Warsaw University Tuesday Seminar Series. And today we have a guest from United Kingdom, Professor Leigh Fletcher, who is associate professor of planetary astrophysics in Leicester. He studied in Cambridge, Oxford, and now he works in both Oxford and NASA JPL, and is an expert in our local solar system, and especially is leading the science explorations with the current and future space missions. So, Leigh, please, the floor is yours.
Okay, thank you so much. Can I just check you can all hear me okay there in the room?
Yeah, all fine.
Fantastic. Okay, so thank you for that warm introduction, and thanks for the invitation as well to come and speak to you today in this virtual seminar. It's a shame I've never actually had the opportunity to visit Warsaw, and I hope that at some point in the future I might get to cross the channel and come and say hello. But for now, at least with these sorts of virtual workshops and seminars, it does give me the opportunity to give everybody there an update on some of the work that we've been doing here in our solar system to try to understand particularly the outer solar system, so the giant planets in my case. Now, I'm aware of you that many of you may not be familiar with the University of Leicester, so let me just give you a quick rundown on some of the stuff that we do here. So Leicester is right in the centre of the United Kingdom. In fact, we pride ourselves in being closer to space, 62 miles up, than we are to any coastline, okay? And we are one of the groups in the UK that works in space science, space engineering, and in my particular case, planetary science. And this is a slide in front of you that's a rather busy slide, but it gives you a flavour of some of the work that we do here at the university in the School of Physics and Astronomy, from missions that we've been part of for several decades, such as the Cassini Huygens mission, which ended its observations of Saturn back in 2017, through to things that are currently active and exploring the worlds of our solar system, such as the current missions in orbit around Mars, the Bepi-Colombo mission on its way to Mercury, the Juno spacecraft, which is currently in orbit around Jupiter, much more on that later on, and things that are just on the horizon for us. So the Jupiter Icy Moons Explorer, JWST, the European Space Agency's first mission to the Jovian system, and of course the James Webb Space Telescope, JWST. That's going to form a huge part of the work that we do over the next 2 or 3 years or so. And finally, looking to the future in the next few decades, I personally hope and I personally believe that we will see a mission exploring Uranus or Neptune in that time scale. So this talk is going to take us through the current work that we're doing in the Jovian system, particularly with the Juno spacecraft. It will look ahead to what we're going to get from the James Webb Space Telescope in the next 18 months or so. And we'll finish by looking to the future with a mission to the ice giants. So broadly speaking, this presentation is going to be split down into 3 sections. I'll first give you my motivations for why we study the 4 giant planets of our solar system. I'll then talk to you about the techniques that we use to take the observations, both space-based using robotic spacecraft, but also large ground-based facilities, large ground-based telescopes. We'll talk about what we've learnt from those facilities, the new discoveries that we're making in the anatomy of the giant planets themselves, and finally we'll look towards the future. So without any further ado, the 4 giant planets of our solar system, this is a scale image showing just how large they are compared to the rocky terrestrial worlds close in, are tremendous places for us to go and visit and explore. In fact, each of them is host to a diverse system of satellites and rings, making each one of the elements within these systems a fascinating miniature solar system that we'd like to go and explore in their own right. As an atmospheric scientist, and I'd look at the meteorology and climate of these worlds, I can tell you that the four giants are wonderful planetary scale laboratories for understanding chemistry, physics, geophysical fluid dynamics on planetary scales, and without the complicated interruptions from things like terrestrial mountain ranges or surface and atmosphere interfaces. This is where pure fluid dynamics really rules the day. Their tremendous size also means that they contain within them the fossils, or the fingerprints, if you like, of the primordial solar nebula. So the material that was out there when these planets were first forming has been locked away inside these giant planets ever since they first formed. And by sampling that composition, by looking at the fingerprints of that chemistry, we can start to understand what the protosolar nebula looked like back during the epoch of planetary formation. I mentioned a moment ago the satellites surrounding each of these planets. Well, a lot of those are now classed as ocean worlds, meaning that they may be geophysically active. They may harbor subsurface oceans of liquid water beneath icy crusts. And as soon as you start talking about water and sources of energy, and of course stability over long periods of time, the question of habitability in the outer solar system keeps coming up. And finally, with the explosion, this pantheon of extrasolar planets and brown dwarfs that we now know of, the four giant planets and their attendant satellite systems are fantastic archetypes and templates, if you like, for some of the worlds that we're discovering beyond our own. Now, each of the missions that we've sent to these destinations have revealed a wealth of new observations, and that's going to be the theme of the talk today. So let's take a look at these two different classes of giant planets that we have here in our own solar system. Broadly, we break it down into the gas giants, Jupiter and Saturn, which are dominated by hydrogen and helium. We think that they formed relatively quickly out of the protosolar nebula. Once the initial protoplanets had formed, runaway accretion then brought the hydrogen and helium gas that was remaining from the formation of the sun itself, and brought with it a few trace species like carbon, like nitrogen, sulfur, phosphorus, and oxygen. And those species then provide the source material, if you like, for all the chemistry that's at work within Jupiter and Saturn today. And Jupiter and Saturn are roughly of the scale of about 10 times terrestrial radius across. Now, contrast that with the ice giants, Uranus and Neptune, which are about 4 times Earth size. These must have formed slightly more slowly, because at the time when accretion was occurring, once the protoplanets had initially formed, there wasn't enough of that nebular hydrogen and helium surrounding those worlds for them to grow to Jupiter and Saturn in size. So potentially the formation of Uranus and Neptune was slower, or maybe arrested at some point in its history before they could grow to be massive gas giants. And that means that their composition is very different from Jupiter and Saturn. They have a lot of the same original elements, but those elements are much more abundant on Uranus and Neptune. They're much more chemically enriched than we see on Jupiter and Saturn. And in fact, where Jupiter and Saturn are so massive that the hydrogen itself can be compressed to form this exotic phase of matter known as metallic hydrogen, that doesn't appear to be happening on the ice giants, where instead, because water is so potentially dominant on those worlds, it might form a superionic slushy mantle of material down at great depth within Uranus and Neptune. So whilst we often lump all of these worlds together into one category, in reality, they're two very different types of planet, the gas giants and the ice giants. And in fact, there are many people who might subdivide them even further still. Now, when we look out at the census of extrasolar planets, and whilst these censuses are still a little biased towards close-in planets that transit across the face of their host stars over short periods of time, a picture is starting to emerge that shows us which are the most common outcomes of the planet formation process. And it's not the enormous Jupiter and Saturn-like objects. It's not really necessarily the terrestrial objects, although that could still be an observational bias. But the peak in the census of planetary radii being detected so far appears to be just slightly smaller than the ice giants in our solar system, the so-called mini Neptunes or mini ice giants, at around about the 2.5 Earth radii in size. So when you look at the physics and the chemistry and the environments that might be present on those mini Neptunes, which is of course just distant objects that we can't hope yet to resolve directly, maybe the ice giants Uranus and Neptune are among our best examples for trying to understand those environments. So we might have in our solar system the most common outcome of the entire planetary formation process, and yet they are very poorly understood and very poorly explored so far. And that's something that I hope the planetary community will be seeking to change in the next couple of decades. More on that later on. Now, the work that I'm going to show you today really continues a legacy of exploration that spans back more than 40 years now, from the era of the Voyager spacecraft, which flew by each of the 4 giant planets, making the most of a rare planetary alignment, to the 90s, where we had the Galileo orbiter and probe for Jupiter, the first and still only time we've directly sampled what a giant planet is made of. I cut my teeth, and most of my PhD research was working with the Cassini spacecraft in orbit around Saturn, studying Saturn's seasons and its storm systems and how it evolved over the course of time. Today, we're working with, of course, the Juno mission at Jupiter, and we're looking ahead to the 2020s and 2030s, which will be the era of Jupiter moon exploration with the JWST mission and ice giant exploration, hopefully in partnership with the Americans. So let's look a little bit more at the Juno mission itself. So Juno launched back in 2011, arrived in Jupiter at Jupiter in 2016, and has been orbiting ever since, conducting long orbits every 50 days or so, where for the majority of the orbit, it's quite a long way out from Jupiter. But then over the span of just a few hours, it screams within a few thousand kilometers of the cloud tops, collecting data as it goes and delivering us some rather stunning observations on these long polar orbits. Juno is the first polar orbiting spacecraft of Jupiter, meaning its views are very different from anything we've had in the past. It's also the first solar powered spacecraft to be orbiting Jupiter. You can see those enormous solar panels which provide it with the electrical energy it needs to take its data. Now, it has a visible camera on there. The camera actually is an outreach and engagement camera rather than being classed as a scientific instrument. But nevertheless, we are able to do tons of science with it simply because of the incredible morphology in the Jovian cloud tops that it's revealing. And here's a selection of the kinds of images that we get on each of the close flybys or perigeos as it screams over the North Pole, and you can see the dappled North Polar domain just there, over the belts and zones of the lower mid-latitudes, and then exits again over the southern pole, where once again you see those dappled storms in the polar domain. And actually, if we put those together as a montage, we can see Jupiter in incredible detail. I think it's fair to say that Juno has really opened our eyes to some of the small-scale processes that are at work on the giant planet. And this is a view taken looking upwards towards the southern polar regions, with the belts and zones being visible off to the right-hand side, punctuated by smaller anticyclones. Now, Juno, one of its key strengths is getting close in views, so it's able to look at the incredible swirling patterns within the Jovian cloud decks that are formed from fresh ammonia ice condensing in the frigid temperatures of Jupiter's troposphere and then reflecting the whiter light back towards us. You can see these swirling patterns prevalent across the entire face of Jupiter, and we're starting to piece together the phenomenology of these meteorological events to understand where they occur, how long they're lived for, and potentially what might be driving them. And of course, the general public is always fascinated by one storm system on Jupiter in particular, the Great Red Spot, shown in this beautiful image taken by Juno just a couple of years ago. So more on that later, but I just wanted to highlight that in addition to spacecraft observations, we also use multispectral observations from ground-based and space-based telescopic facilities. And the reason that we try to do that is because different wavelengths of light will probe down to different layers of the planet's atmosphere. From high up in the stratosphere and thermosphere, where things are controlled by the radiative balance of energy absorption from the sun, to down in the convective weather layer of the planet, where all that churning motion is taking place and shaping the clouds that we can see. In fact, on Jupiter, in this particular collection, these images that you see in front of you span several hundred kilometers in terms of vertical extension through the atmosphere. And so a lot of this remote sensing is pushing towards attempting to reconstruct these atmospheres in 3 dimensions so that we can then understand their climate and meteorology via comparison to numerical simulations and models. Now, of course, underlying all of those gorgeous images are spectra. And this is the key element that I use for my research, remote sensing of spectra from the visible out to the microwave range. And I'm just going to talk you through the 4 panels that you have just here. On the left-hand side are the visible spectrum and the near-infrared spectrum from VIMS observations of Saturn in this particular case. And what you have in reflected sunlight, as far as about 3 or 4 microns, is a mirror for the sun's solar spectrum with gaseous features within the planetary atmosphere eating away at that sunlight. So where you see a trough within these spectra, it's because there's a particular gas, mostly methane, that's absorbing all that sunlight and preventing it from being reflected back. So you can read a reflected sunlight spectrum in terms of where the light is being reflected in that atmosphere. On the right-hand side, you have thermal emission taking over from reflected sunlight, broadly from about 5 microns and longward through the mid-infrared, the far infrared, and the microwave. What you should see is a smooth undulating continuum that's formed by the collisions of hydrogen and helium molecules. Now, they don't have an instantaneous dipole, which would give them a nice sharp spectral feature. But when you have enough hydrogen and helium, it can bang together to form something called an instantaneous dipole. And that instantaneous dipole means that you have an opacity source, which prevents you from seeing any deeper down than, say, roughly the weather layer, the cloud forming region. Now, if that would be the case, if you had only hydrogen and helium present, in reality, we have all these trace species mixed in, and anything that's doing its primary absorption in the troposphere will create an absorption feature because the center of the band is at a colder, higher altitude than the surrounding window. Whereas anything that's doing its prime contribution in the stratosphere will create an emission feature. So we have absorption features from things like phosphine gas, pH3, ammonia gas, NH3, and we have emission features from methane gas and all of its derivative photochemical products, lots of hydrocarbons being produced by the chemistry at work high up within these planetary atmospheres. And so by fitting spectra in reflected sunlight and thermal emission, we can measure things like the temperature, we can determine how much of the gaseous species are there and how they vary with space and time. And we can look at how the cloud structure forms on the giant planets and how they're distributed, again, with space and time. So that will underpin a lot of the discoveries that we're making in the rest of this talk. And just to give you a flavor of where we are today with infrared remote sensing of the giant planets, I've just pulled together a montage of my favorite images of these worlds today at different wavelengths spanning between about 5 microns and 20 microns. Jupiter on the left-hand side there, Saturn from the Very Large Telescope. In fact, all of these are from the Very Large Telescope in Chile, up at Paranal in the Atacama Desert. And you can see that as we go further and further away, the spatial resolution of our observations gets lower and lower. And actually, to do Uranus and Neptune science properly, it's extremely challenging because these objects are so far away and so cold that the black body emission that we're detecting is roughly the same equivalent temperature as about 50 to 60 Kelvin. Okay, and we're detecting that from 20 to 30 astronomical units away. So these are the best images we have of Uranus and Neptune at these long wavelengths. Be prepared over the next 18 months or so for the James Webb Space Telescope to blow these images out of the water. So, having given you a flavor of why I'm interested in studying the giant planets and how we go about doing remote sensing of these objects through imaging and spectroscopy, let's now get back to basics in terms of what we're actually looking at on each of these giant worlds. So we mentioned at the beginning that they're accreted out of the protosolar nebula, so they're dominated by hydrogen and helium with all the other cosmogonically common elements then mixed into that soup of material, if you like. Now, because there's so much hydrogen, all of the minor elements, carbon, oxygen, nitrogen, sulfur, phosphorus, you name it, they're all in their reduced hydrogenated form. So we find them as methane, we find them as ammonia, we find them as water. Now those volatile elements can then go on to condense to form cloud decks. And unlike Earth, where we have just one key volatile, water, that's condensing to form our cloud decks, on the giant planets, we have multiple layers of cloud decks, depending on when the partial pressure of a particular gas exceeds the saturation vapor pressure. So on Jupiter, for example, you have an ammonia cloud, which is the topmost layer. Below that is a blend of ammonia and hydrogen sulfide, the NH4SH cloud. And below that, you then get a water cloud. The water cloud is largely hidden from us because of the overlying clouds. And perversely, that means that the oxygen or the water in the upper troposphere and stratosphere is very, very hard to detect because it's all locked away at greater depth down below the base of the water cloud. Now, anything that doesn't condense, and on the giant planets, methane is the key species to think about, is then subjected to UV photolysis in the stratosphere and upper troposphere. That splits apart the methane molecule and recombines it into long chain hydrocarbon species. If for some reason you then add nitrogen into the mix, you can form nitriles as well. And high up, we even have an influx of exogenic oxygen species. Think things like interplanetary dust or micrometeorites or even large cometary collisions that bring in oxygen and then can contribute to the photochemical chain. All of this adds up to a very complicated chemistry high up in the planet that's driven from thermochemistry below, condensation chemistry in the clouds, and then photochemistry above the cloud decks. And just to make matters even more complicated, all of this is being churned up by the overturning circulation patterns within the atmosphere, bringing up species from down at great depth up to the levels where we can detect them. And one such example is phosphine gas just there. So if you mix this all together, in the vertical, we can split a planetary atmosphere up into multiple layers. From the interior, where the vapors are not saturated, it's moist and it's being driven by potentially energy sources from down at great depth, into the upper troposphere, where you get the condensation clouds forming, and that's where we really see all the weather and the churning cloud activity that you can see through a telescope. The middle atmosphere, where all the chemistry is occurring, into the upper atmosphere in the rarefied upper levels of the planet, where it's interacting with the external magnetic field environment. So we can break that down even further into radiative dominated layers, to meteorologically dominated layers, and then dry, deeper layers, which we're only just starting to get a glimpse of with things like the Juno spacecraft. So let's talk a little bit more about the dynamics then of these planets. And this wonderful movie that you see playing on the screen was developed or created by the Cassini mission as it flew past Jupiter in the year 2000 on its way out for its encounter with Saturn. It observed Jupiter over several days and could watch as the winds were blowing the material around from place to place. You see the traditional candy-colored stripes of Jupiter, and we still think to this day that the whiter material is fresh ammonia ice condensing that's been brought upon updrafts, regions that we might call zones, whereas the darker material is regions where the ammonia has been sublimated away, leaving darker brown material down at depth. So what you're seeing there is a three-dimensional circulation pattern with winds zipping east and west, keeping things separate, and air rising and falling, causing the different colors. Now, we know other worlds where this sort of thing is happening. So that Met Office diagram on the bottom left shows circulation cells within our own atmosphere, the Hadley cell being the most famous, with air rising at the tropics, moving towards the poles and conserving angular momentum to create subtropical jets over the Tropic of Cancer and Capricorn. And what comes up must ultimately sink back down again, and that drives the famous trade winds over the Atlantic and Pacific Oceans. In between the poles and the Hadley cell, you have something else called a Ferrel cell, which is driven by the energetics of eddies and storms cropping up within those regions. So can we apply what we know from terrestrial meteorology to giant planet meteorology? Well, we can. If we look at the temperatures on the top row and then ammonia gas as a tracer for those upwelling and downwelling motions, we see features and structures that are familiar to us from looking at terrestrial meteorology, namely, for this diagram, equatorial Hadley cells. So rising motion at the equator and sinking motion in the neighboring north and south equatorial belts. So that rising motion brings ammonia up from below, the sinking motion pushes it back down again. So the temperatures and the contrast that we see in ammonia are consistent with a Hadley-like circulation present at low latitudes on Jupiter. In fact, one of the earliest discoveries of the Juno spacecraft, using microwave light that peers down below the cloud tops of Jupiter, was that you actually have this deep column of ammonia rising up from hundreds of kilometers down within the planet's atmosphere. So what we see at the cloud tops is just the tip of the iceberg, below which sits this complicated circulation pattern. So just to reinforce, upwelling at the equator and downwelling at the north and south equatorial belts just there. But what was going on at mid-latitudes? Well, again, step in the Juno observations themselves. So let me just talk you through the diagram on the left-hand side here. Here we have a visible light image on the far left, taken by the Hubble Space Telescope. The cloud top winds as measured by the Cassini mission on the right-hand side, and you can see them zipping between eastward and westward flow on this diagram. And then in the middle are two slices of the microwave brightness measured by Juno. One of them is taken just above the water cloud, and another is taken just below the water cloud. You can see that they're all striped, okay, and that features line up from one to the other. But the weird thing is that the microwave contrast changes from being above the water cloud to being below the water cloud. So something like a belt that was bright in microwave light at shallow depths becomes dark in microwave light at deeper depths. And this was a bit of a surprise. Now, those microwave belts and zones, if you like, line up perfectly with the belts and zones that we see at the cloud tops, and they line up perfectly with the zonal winds themselves. So this is a system, a circulation pattern, which appears to not only be present at the cloud tops, but also down at greater depth. And a simple, I should say, maybe complicated cartoon for what's going on is given by the right-hand side just there. Now, everything we knew before the Juno mission pointed to circulation patterns that were similar to what's going on in the so-called upper cell just there in the cloud decks, where zones were regions of rising motion, adiabatic cooling, and when you cool things down, stuff condenses, so they look cloudy and white. The belts, therefore, were regions where the air was sinking, warming up, resublimating those clouds and appearing darker red. So that's like the canonical view of belt zone circulation that had been around for decades. There had been some hints before Juno that things weren't quite as straightforward as that, but Juno has now revealed that if you go down below the water cloud, it looks like that circulation pattern changes direction. The belts become enriched in ammonia gas, meaning that you've got material that's being brought up from below, and that makes it microwave dark. So we have like this clockwork pattern of overturning circulation cells. And these have been likened, at least in the deeper levels, to ferrule cells that we have here on planet Earth between the Hadley cell and the polar cell. And just to give you a nice cartoon that was prepared by Karen Dewar and the team to show what this comparison might look like. You've got those cells that we talked about earlier for Earth on the left-hand side, but on the right-hand side, you have these multiple smaller ferrule-like cells, each one being associated with one of the jet streams of Jupiter. So how can we understand this? Why does Jupiter have more cells on it than the Earth? And it all comes back to fluid dynamics and meteorology. The faster you spin a planet, the more of these belts and zones or ferrule cells you can fit in between the equator and pole. And if you go to the opposite extreme, to something like Venus and Titan, which are only rotating extremely slowly, the Hadley cell can then expand to go from the equator all the way up to the pole. So the faster you spin, the more of these ferrule-like cells you can get in between the equator and pole. And Juno has shown that these ferrule cells are not constant as a function of depth, but actually appear to flip in their character as you go down below the water cloud. So that raises the question of how deep do the belts and zones actually go? The microwave light only penetrates some 300 kilometers down into the planet itself. Well, Juno has another technique for exploring what's going on down at great depth, and that is by looking at the gravitational acceleration being sensed by Juno as it's orbiting around the planet. And the tiny density perturbations that it's measuring as a consequence of the fast flows through the atmosphere, they're being detected and they have been modeled, and they suggest that the winds extend some 3,000 kilometers down. Don't forget, Jupiter is some 70,000 kilometers in terms of radius. So it still is just the upper layers. So what's going on about 3,000 kilometers down that stops these zonal winds from flowing? It appears to be the transition from regular gaseous hydrogen to the metallic hydrogen that's conducting. So the transition to that weird exotic metallic hydrogen down at great depth may be controlling the depths of the winds. And to make that sort of discovery, you really needed Juno there in the system, able to sample the depths with these multiple different techniques. Now, just to give you some more of the headlines from the Juno spacecraft, of course, I couldn't resist showing you some more of the images. This is the Great Red Spot captured in 2019, a swirling anticyclonic vortex in the southern hemisphere of Jupiter, where the entire of planet Earth would fit quite nicely within that red circulation pattern in the center. To this day, we don't know what the chemical species is that creates the red color. There's plenty of ideas, but no unique spectral signature of what that material is. Although we do know that as the Great Red Spot is buffeted by incoming storms and anticyclones from elsewhere, some of that red material can be extruded from the top of the Great Red Spot. So I like to think of it as being just a superficial red coloration. Think of it like looking at storm through an orange filter sat over the top of churning lower cloud decks. It's quite easy to disturb that top red material without actually disturbing the deeper underlying storm system, which we know has been raging for at least 150 years, if not longer. In fact, it's almost 200 years now. It was first sketched in the 1830s by Victorian astronomers. So we know this storm has been raging for an extremely long time, and it's possible that things like phosphorus or other chemical species might be causing that red color. So from anticyclones at low latitudes to the biggest surprise of the Juno mission so far at the highest latitudes. Now, don't forget, nobody had been able to get a good image of the poles of Jupiter before on any previous spacecraft, and of course, not from the Earth, because Jupiter has a very tiny axial tilt. And when we finally got our glimpses of the northern southern poles with the Juno infrared observations, we caught a octagonal crown of circumpolar cyclones surrounding a central polar cyclone. And that octagonal crown has been relatively stable throughout the 6 years of the Juno mission so far, only experiencing light perturbations from the storms surrounding it. This is a fascinating structure that an entire lecture could be devoted to, but I just want to point out that at the South Pole, even stranger things are going on, where at the beginning of the Juno mission, a pentagon of circumpolar cyclones was observed, and every now and then that can transform when an interloper manages to squeeze itself into a hexagon of circumpolar cyclones, although that doesn't appear to be a very long-lived state. And if you're wondering, when I say about octagons and pentagons and hexagons, whether this has got anything to do with the hexagonal wave at the North Pole of Saturn, you would be right, because the meandering of the North Polar jet stream that forms Saturn's hexagon may be just a different manifestation of the kind of dynamics which is forming these circumpolar cyclones. Now, in addition to the Juno observations, we take data from Earth over the long spans of time. In fact, this particular chart goes from the year 2000 through to 2017, and I include it to show how important amateur observers are to the study of long-term dynamics within the Jovian atmosphere. What you might be able to see there, if you look at the dark north and south equatorial belts, so immediately north and south of the equator, is that the north equatorial belt expands and contracts over time with a period of about 4 years. The south equatorial belt can sometimes vanish entirely, like a haze of white material forms over the top of it. And this happens on a period anywhere between 7 and 14 years. We haven't seen one now since about 2010 or so. Now, these long-term cycles, we're only starting to get to grips with because we have data sets, databases that span sufficient amounts of time. And one of them in particular that we studied very recently was known as an equatorial cloud disturbance. The clouds at Jupiter's equator are normally bright white in color, and that's the sort of canonical picture of Jupiter that you'd be able to get off Wikipedia or anywhere that you might choose to look. Those white clouds block infrared light from below. So that example in 2016 is what Jupiter normally looks like. But every 6 to 7 years or so, something weird happens where the white cloud material over the equator disappears to be replaced by churning activity that appears to be deeper down. And because the white cloud has disappeared, we now get a huge amount of bright emission in the infrared that looks completely unlike the canonical view of Jupiter. And even today, there is evidence that the equator is still disturbed after the last cycle in 2019-20. So that was something that we could only study by having a data set that went from the early 1970s, these observations at 5 microns infrared light, through to the present day by seeing the cycles of activity within there. And it begs the question of what is controlling some of these long-term cycles that we see on Jupiter. We've got timescales of 4 years, of 8 years, of 14 years, and potentially even longer that we haven't detected yet. Could this be something deep in the interior controlling things? Or are waves propagating through the upper atmosphere and middle atmosphere somehow causing these particular periods to come out? Now, of course, the Earth's atmosphere has cycles and periodicities which we're still working to understand, such as the El Nino Southern Oscillation, the North Atlantic Oscillation, the quasi-biennial oscillation. These oscillations within a climate systems have been described as the natural heartbeat of a planetary atmosphere. And it seems that all planets have some kind of regular pattern like this, but we don't fully understand the drivers of those. And I'd say we're in the stage of characterizing the phenomena now, and understanding what's controlling them will be the next step in this research. So the Juno mission is still going today. It started an extended mission in 2021 after a wealth of scientific discoveries having been made during its first 5 years. The orbit is evolving. So the closest approach to Jupiter used to be near the equator, but with every single one of these close encounters, we step a few more degrees of latitude up. And as the latest perigeos that are planned in the mission should actually have closest approach over the North Polar region. So our views in microwave and infrared light of the polar domains are only going to get better over time. The really cool thing about that change of inclination is that it also has opened up the opportunity for flybys of the satellites of Jupiter, which was something that wasn't really planned in the first days of the Juno mission, and shows what you can do with a New Frontiers class orbiter. Ganymede was encountered last year, and there's a whole wealth of data that came from that. Europa is coming up soon on perigeo 45, and late in the mission we'll get some great views of Io as well. So watch this space. That brings me on quite nicely to the future of the observations of the outer solar system. So most of what I've discussed there has been dealing with Jupiter, because that's the big thing that's been on our mind for the last 5 years with the Juno spacecraft. But of course, on Christmas Day of 2021, after nearly a quarter of a century of development, the James Webb Space Telescope finally launched out to its lonely vantage point at the second Lagrange point. It took about 30 days to get from that launch out to the Lagrange point, and ever since, it has been deploying, calibrating, and making sure that all of its instruments work. As you might remember, James Webb had to be launched in a folded configuration, and then both the telescope itself, 6.5 meter wide, made of hexagonal segments that are gold plated to reflect the infrared light, had to unfold, and the sun shield, which is the size of a tennis court, required to keep the entire observatory cold, also had to deploy in space, possibly one of the most complicated deployments of any spacecraft yet sent. And incredibly, it all seemed to work flawlessly, to the extent that today we've had the first images from each of the instruments on board James Webb. In fact, this was looking, I believe, at the Large Magellanic Cloud. And if you zoom in on the detail of the MIRI instrument, which is the instrument that covers those wavelengths that, frankly, I really care about, beyond 5 microns, you can see the improvement we get from previous Spitzer observations to what the MIRI instrument has been able to do in the form of imaging. This is at 7.7 microns, so you can see lanes of dust and material with the foreground stars shining brightly just there. Now, it's fair to say that people didn't expect things to go quite as well as they have been going, and seeing images of this kind of quality really did bring a tear to the eye, because it really whets the appetite for what we're going to be doing over the next few years. And in fact, the stunning news was that that launch was so flawless that Webb has the fuel to potentially go for 20 years. So this could define an era for astrophysics and planetary science over the next couple of decades. Now, what I'll be doing with this particular facility is making the most of integral field spectroscopy. And it's relatively new concept. It's been used on ground-based facilities, but this is the first time, I believe, on a space telescope, where you take the scene, you split up the scene into individual slices, and then from each of those slices, you disperse the light to form a spectrum. So the field of view placed over something like Uranus there on the bottom left-hand side would then be each split up into 10 to 20 individual slices. Those slices are then dispersed onto a detector, and that's where you see all the individual spectral features. And then those dispersed spectrograms are then recombined to form an image cube that spans the entire spectral range of James Webb. In fact, there's a near-infrared instrument called NIRSpec between 1 and 5 microns that will do this, and the mid-infrared MIRI instrument does this between 5 and 28 microns. The beauty of this for a planetary atmosphere that's constantly changing and evolving is that you get both spatial information and spectral information all at the same time. Normally, we do one or the other. You take great images to freeze frame the atmosphere at that particular moment, or you have to scan a spectral slit across the scene, but then, of course, you worry that the atmosphere itself is changing beneath. So James Webb can actually do this all at once with an IFU. That's wonderful. But the problem is that it has very small fields of view. And this is actually one of the more optimistic fields of view compared to the size of Uranus and Neptune in the top left just there. But you can see for objects like Saturn, we have to mosaic to get any spatial information across the disk. And for Jupiter, the Great Red Spot fits just about into a single one of these footprints. So that's a bit of a challenge, because we'll have to make large scale mosaics of a big, rotating, moving, and very bright object from Webb's perspective. But when we do, we'll get stunning spectra of these to the extent we're going to have sensitivity on some of the darkest regions of the spectrum that not even things like Voyager or Cassini ever had in the past. So the ice giants are really going to be a playground for the JWST observations, because their stratospheres are so cold that no previous spacecraft has ever really been able to make a dent in understanding them. These are simulations based on our current best understanding of what they might look like, but they are just educated guesswork. And in the next few weeks and months, when we start getting the multispectral images down, we'll be using the temperature and gaseous and aerosol distributions that we can derive from these sorts of spectra to measure the circulation patterns within the ice giants, to understand their global composition, to try to back out where they might have come from. And of course, all of this is about raising the maturity of ice giant science so that it meets what we currently know for Jupiter and Saturn. And just to show that I'm not only interested in the mid-infrared, in the near-infrared, where, remember, it's the reflected sunlight spectrum with methane eating away at the solar reflection, we also have NIRSpec taking some fantastic data. And between about 2.5 and 5 microns, we know very little about what the ice giant spectra look like, other than the fact that we should see H3 plus emission, an ion high up in the thermosphere of these worlds, not detected yet on Neptune, but certainly just about detected on Uranus. And who knows what other crazy fluorescent effects we might see in those NIRSPEC observations. So I'm extremely excited to see what they may entail. Now, unfortunately, because we're carrying a whopping great sun shield on our back to keep the observatory cool, you can't point James Webb Space Telescope directly at a planet at opposition when the resolution might be best. You can't look anywhere in the sky. You have to look in certain locations, ensuring that that sun shield on your back is keeping you cool all of the time. And that means that there are seasons when we get to observe a planetary target. There are two of them, and roughly they align with the quadrature point. So when it's at about 90 degrees between the sun, Earth, and target line. Okay, so those quadrature windows, roughly about 50 days long, are when James Webb is going to be able to take the data. And the latest update that we have from those who are planning the data is that all the commissioning of the instruments is going to be complete, hopefully by the early summer, by around about June. Then Jupiter is in the right place to be an early target. We're hoping to get observations of the Great Red Spot and poles in June of 2022. Then Saturn will come along later in this year and be in the right place for October to November. Uranus before that in August and September this year. And then Neptune will be observed in June of next year. So just about 12 months down the line. So we have our work cut out for us, but we are going to have some tremendous images and spectroscopy of each of these worlds that will really blow the existing state of the art out of the water. Now that brings me to the next big thing, I think, in planetary exploration. And I'm just going to wrap up in the next 2 or 3 minutes to leave some time for questions. And that is that the US Decadal Survey in Planetary Science and Astrobiology recently reported back and have prioritized a mission to an ice giant, in particular the Uranian system, as their next priority for the coming decade. And this is something that we in Europe and in the United States have been working to for many, many years as the next sort of logical step in exploration of our solar system beyond the Cassini mission to Saturn. Don't forget that although Voyager did fly by these worlds back in the 1980s, it did so with just a fleeting glimpse of these very changeable, variable, and incredible targets. So what we're hoping to do is try to understand the formation conditions for the ice giants, how they differed from the gas giants, to teach us something about the most common outcome of the entire planetary formation process. We're going to Uranus in particular because it experiences the most extreme changes in solar insolation and solar wind and magnetic field conditions of anywhere in our solar system. And of course, if you want to test a physical or chemical theory to breaking point, you go to the most extreme places to do so. The satellites that surround Uranus are believed to be ocean worlds, potentially with subsurface oceans and potentially with geophysical activity, not just in the ancient past, but maybe ongoing today. And if that's the case, if there is active worlds, active ocean worlds in the outer solar system, then that may push the limits of habitability much further than we've ever appreciated in the past. Now, these missions will be, by their nature, very long term, meaning that we're hoping that a big strategic and collaborative mission to the ice giant system Uranus will inspire the next generation of planetary exploration. Uranus in particular, the last view that we had of it back in February 1986 left a huge myriad of questions behind for us to one day go back and explore. And the thing that, as a decadal survey, they really liked about a mission to the Uranian system were the cross-cutting interconnections between all the different themes. A Uranus mission doesn't just keep individual planetary scientists happy. It will be of interest to astrobiologists, to heliophysical scientists looking at the connection between the solar wind and planetary environments. It hopefully is appealing to the astrophysicists studying extrasolar planets, given that these worlds might be a great template for those sorts of environments. And of course, for anybody who is interested in trying to probe the early history of our solar system, explaining why the ice giants formed at the size and location that they did is a missing piece to this puzzle. So hopefully, if everything goes to plan, in the next decade, we'll be launching a mission from the Earth to Uranus to make the most of a Jupiter flyby in the mid-2030s to give us that extra gravitational kick to get out to the ice giants. Then within 12 to 13 years, it will get into orbit around Uranus in the early to mid-2040s for a 5-year mission to explore the fantastic Uranian system and the planet itself to try to address all of these questions. So really is a mission for the next generation. I personally hope that the European Space Agency and national agencies within Europe all decide to get engaged in this US-led mission in the same way as we did with Cassini-Huygens back in the 80s and 90s. If that all feels like a little bit long to wait, then one thing I haven't had the time to talk about today is ESA's Jupiter Icy Moons Explorer, which is so close now to getting to the launch pad. The target launch date is April of 2023. This will be Europe's first mission to Jupiter. We'll get there in about 7.5 years after launching, so early 2030s. And at the end of the mission, it will become the first robotic orbiter of an icy moon, the moon Ganymede. So hopefully that whets your appetite for things to come. And if I was to just briefly summarize what we've talked about in today's lecture, we talked about the Juno spacecraft and how it's continuing to explore the atmosphere, interior, and magnetosphere of the solar system's largest planet. I hope I've whet your appetite for the forthcoming observations of all 4 giants and their satellites from the James Webb Space Telescope. And I also believe that today, a partnership, an ambitious international partnership mission to the Uranian system is really within our grasp. So with that, I'll thank you very much for your attention. I hope that's given you a flavour of the research that we do here at Leicester, and I'd be happy to answer any questions you might have.
Thank you very much. Indeed, that was indeed very inspiring and good questions. And I will ask you to come forward because our microphone is here.
Hello, thank you very much. I have a few concerns regarding the impact events on Jupiter. First of all, if you could detect, and did you detect, have you detected them with Juno? And another thing is that to what extent can they affect the composition of atmosphere, and if it is a detectable effect at all?
Right. So the question was about impactors into the Jovian atmosphere. And of course, the most famous example of a planetary impact was the Schumacher-Levy 9 impact back in the 1990s, where a comet that had been broken up by Jupiter's gravitational field went slamming into the south polar region of Jupiter over the course of about 5 days. And it left tremendous scars on the cloud tops of Jupiter. And when we used spectroscopy to analyze the contents of those scars, we found silicate and silica minerals left over from whatever rocks were within there. We found gases that had no right to be in that particular location, potentially dredged up by the energy of the impact itself, but maybe also delivered by the comet. So for example, we saw things like hydrogen cyanide, carbon monoxide, some materials that could have been produced by the chemistry of those impacts. And those chemicals, although the scars faded, the chemicals hung around for years, and in fact are still present today within the atmosphere of Jupiter. Now, since the 90s, the Schumacher-Levy 9, we've had one other massive impact, which was an asteroid in 2009. I was out at JPL working at the time, and we got time on a telescope. We did about 10 hours of some amateurs alerting us to that case. And we did the same thing, take spectroscopy of the scar to try to understand what had happened. But amateur observers now, frequently they take their data by taking video movies of the scene, and then they stack together the sharpest images. Often they then throw away the movies, but we've been persuading them not to, because in those movies, you can detect impact flashes. And something on the order of, I believe we're up to about 7 or 8 of these bolide events, so shooting stars within the Jovian atmosphere, have now been detected, not by big telescopes or spacecraft, but by the amateur community. And finally, you said about, has Juno seen any? Well, I'm not entirely au fait with the particular paper, but I'm aware that there was a flash event observed by the UV spectrometer on Juno, which had all the right timescales and properties to have been another one of these bolide events captured by the Juno spacecraft itself. But if you think about the configuration, about when Juno is observing, you have to have hit it so luckily to actually see one of these impact flashes. Whereas, of course, long-term monitoring, like the amateurs are doing, it's the best way of picking them up. Not detected on Saturn yet, to my knowledge. So that's the next frontier. Yeah. You're welcome.
So hello, and I just wanted to say what a beautiful and visually engaging presentation. And
Thank you.
My question is that with those spectral observations that you've talked at the end of your presentation, since they are limited with Jupiter and Saturn, I wanted to say if there are any areas of particular interest or that are better to observe, since as we can clearly see, those planets are not chemically homogeneous.
Yeah, that's a really good question. And so the guaranteed time observations of Jupiter and Saturn in particular, we've been planning for about 5 years now, and trying to, it's not just a scientifically valuable thing to do, but because Jupiter and Saturn are so inhomogeneous, as you mentioned, it's a test for the facility as well, to try and understand whether we can track a feature on the disk of Jupiter. We've chosen the Great Red Spot as a first test, because even with that, we need to mosaic. What we're trying to do is detect the chemical fingerprints of whatever signature is making it red. But we've also going to target the South Polar domain, where you've got an interface between energetic electrons coming into the atmosphere, heating up the polar aurora, and then the chemistry of the atmosphere being seen in the stratospheric emission. So the South Polar region and the Great Red Spot we chose to look at, but we could have chosen lots of other locations. Then on Saturn, Saturn's a little bit further away, so mosaicing is not quite as difficult for Saturn. So what we're doing there is we're stepping down from the North Pole, where the hexagon is located, down towards the equator, where at the equator we have another one of these planetary heartbeats, these oscillations that I was mentioning about earlier on. And the observations should happen 5 years, almost to the day, after the demise of the Cassini spacecraft. So in that 5 years, Saturn's seasons have sort of marched on. So we'll be comparing what we see with Webb to what we saw with Cassini at the end of the mission to understand how the seasons have evolved with time. Okay.
Thank you.
I was intrigued by the involvement of amateurs. You mentioned them on a couple of occasions. Could you elaborate a little bit more about this? What are the requirements? What is the network? How do you coordinate it? Are you doing it via your Twitter account we see on your slides, or how do you do it?
So I can take no credit for the coordination side of things, but what has happened with the advent of social media is that a self-organization of amateur observers has started to occur. And a particular group out in Bilbao, some good friends and colleagues of mine at the University of Bilbao, set up something called the PVOL, the Planetary Virtual Observatory and Laboratory. And they ask amateur observers who are looking at Jupiter on a nightly basis to upload their images with a timestamp so that it's helpful for future observers to this database. And there's a gargantuan database rich in atmospheric dynamics as a consequence. And several tens of papers have come out from that Bilbao team looking at the changing atmosphere of Jupiter. There are, of course, that does tend to focus more on Western observers, I should say. And so in Japan, there's another database called Alpo Japan. And Alpo Japan also has a huge number of contributors, primarily from Eastern regions. And so between them, Alpo Japan and PVOL, we have a rich resource to go and look at. And in terms of equipment, it's very easy to get dismayed when you look through your own telescope at one of these targets if you're using anything sort of smaller than, I don't know, a 5-inch or something like that. A lot of the best amateurs in the world are using things like Celestron 14s, okay, and they're getting gorgeous observations and resolving features that we can then track, and that's the key thing. But I would urge anybody who thinks that they've got a resolved image of a giant planet from their observatory to upload it to the database, because you never know when it might just fill in a tiny piece of the observational record when something happened, something that was out of the ordinary or unexpected. So yeah, don't be disheartened if it's not up to Hubble quality in terms of those images, but they are still extremely valuable for us.
I think we lost you.
Okay, I can hear you again. I think we had a temporary dropout there, didn't we?
Yeah, it was our fault, I think.
Any further
back
questions
now.
then? Yeah.
Thanks. Any further questions? I don't see any. I don't see anything on Zoom here. So thank you, Leigh. That was really inspiring, and as Kasia said, visually really pleasant to watch. So thanks for bringing us up to date with the current state and also showing us the very bright future of this part of the research. So let's thank our speaker again.
Thanks very much, and I hope you all have a great rest of the day.
You too. Okay, thanks. Bye.
Bye-bye.